cells. National primary standard, which we have at National Physical Laboratory, was a foundation towards PV quality infrastructure in the country. We have with us Professor Dr. Sanjay Srivastav. He is the principal scientist, senior principal scientist at National Physical Laboratory. He has a lot of experience in the National Physical Laboratory, and he's an honorary professor in the Academy of Scientific and Innovative Research, ACSIR. He has been working in the development of solar photovoltaic devices, testing and calibration, and related applications for more than last 18 years. He has made scientific significant contributions to develop black SIPV device concept and also established several key facilities at National Physical Laboratory for silicon, solar photovoltaic and related energy applications under mega projects initiated by CSIR. In addition, he has executed several projects on silicon PV related with PV and related aspects at National Physical Laboratory. He is a young recipient of prestigious Young Scientist Award in Physical Sciences in 2013 for his contributions towards development of black silicon solar cells by cost-effective light trapping schemes. Sir, thank you very much for accepting our request. He has been visiting fellow to PTB Germany, and he has written more than 100 scientific articles and 10 book chapters. He has done a lot of guided several PhD and master research students, etc. Thank you very much, sir, for accepting our request and delivering this lecture on a very important topic, which is actually very important for us, for Indian point of view, because we are developing more and more solar voltaic cells, large number of installations, and the establishments are being happening. Whether we will be able to have that energy even after 25 years, it is a very important task. As we are thinking that, today, if we are establishing this facility, this will continue for 25 years. So these things are very important. I hope that with this lecture or after this lecture, our participants will be benefited from your knowledge, vast knowledge and experience. Thank you very much, sir. Sir, we have with us our Honorable Shri B.N. Dixit, Director, Legal Methodology, B.N. Dixit Sahab. Sir, would you like to speak 2 words, please?
Yes, Ashutosh Agrawal ji.
Thank you, sir.
It is
Please.
matter of very great pleasure that you are selecting the different topics on the science and the measurement of science. Apart from SI system of units, that how to do the calibration, how to do the testings. I think in the solar measurement, it is the same as you are doing for the electrical measurement. Only the process may be very bit different. So otherwise looks same. So this is matter of great pleasure that today topics we are having on the solar measurement. Government of India has taken decisions for the implementation of solar measurement throughout the country, and various places the people are adopting the solar measurement. Even in the public also through banking systems, lot of loans are being given for the implementation for installation of solar measurement systems in the houses. So it is not only in the government department, but it is also on the private houses. The solar measurement facilities are there. With this very word, I wish for the success of the programs. I hope that under Dr. Legal Metrology, Sri Ashutosh Agrawal, all these things will be flourish, and I wish for the success of the program. Thank you, Ashutosh.
Thank you very much, sir. Thank you for your kind and motivating words. Thank you very much, sir. We are always looking towards you for any type of motivation. Thank you, sir. Thank you. Over to you, sir. Professor Dr. Sanjay Kumar Srivastava, sir. Over to you, sir. Please.
Thank you, sir. At the beginning, let me thank the legal metrology team led by Ashutosh Agrawal ji for giving me this opportunity to share some of our recent efforts at CSIR-NPL with this August gathering through webinar mode. And also, I'd like to thank our, senior scientist, Dr. Sanjay Yadav, for coordinating this with legal metrology very efficiently. So in the next 60 minutes or so, sir, I will talk about the National Primary Standard Facility for Solar Cell Calibration, which has been established at CSIR-NPL, and we consider that this as a foundation toward PV quality infrastructure in the country. Sir, am I audible properly?
Yes, sir. Very well. Please.
Okay, thank you. So I will try to sensitize the audience about the solar photovoltaic technology and its importance in the country in view of the energy challenges of the country, and also about the compliance towards the unbroken chain of traceability of the measurements of
Picture at the top may
devices,
also may be
photovoltaic
slightly.
devices, so that we have accurate estimation of the performance of the devices, and there is no loss. And what is the status of the photovoltaic technology in the country, and what role CSIR NPL can play or playing in this the success of the national solar mission in the country. So, okay. So the brief outline agenda of my talk today, I will start with a brief introduction to NPL, though NPL is known to everyone, and then our photovoltaic group. Then I will start with some basics of PV solar cell, because audience may not be of the same field. So I'll try to keep it as simple as possible. Then PV modules and R&D, research and development efforts at CSIR NPL in this direction, energy scenario of the country and the importance of solar PV technology, as I mentioned in India, also about the national solar vision of the country, plan and current status of the solar PV installation in the country, need of a strong PV quality infrastructure, which is the main theme of today's talk. That is the PV metrology and traceability chain in the PV devices, how it works, and then in the last segment, I will talk about our national primary standard facility for calibration of solar cell and the current status of the facility and what we think for the future. So with this, let me briefly tell you about the organization I belong to. Of course, I belong to the CSI National Physical Laboratory, which is one of the 37 national laboratories under the umbrella of Council of Scientific and Industrial Research under Ministry of Science and Technology, Government of India, it is the premier physics laboratory, which is doing cutting edge research in the basic, fundamental, as well as applied areas. And we have a very, this institute is also mandated to be National Meteorological Institute of the country, because it has got mandate to maintain, develop, maintain, and disseminate the national standards of all the physical parameters in the country. So it is NMI. In addition to that, we have a very widened program, research program in advanced materials development, devices, and their metrology as well as. And in this division, we have very active activities, research activities on the photovoltaic, right from first generation silicon solar cell to the third generation, or you can say next generation solar cell concepts like perovskite and organic solar cell and so on and so forth. So we have in our PV metrology group, which is very well equipped with solar cell materials, device fabrication, and their measurements. Here are some certain list of the important components. I will not go into detail of this list. These are also available on our website for the sake of time. And we have a team of 8 scientists supported by 3 technical staffs and number of PhD students. We have almost a state-of-the-art clean room complex having class 100, class 1000, class 10,000 cleanliness, and we have a number of R&D projects funded by DST, SERB, Nanomission, DST Nanomission, MNRE, CSIR, Ministry of Power and consultancy projects from different industries. And recently, we were given the responsibility of setting this PV metrology in the country, that is National Primary Standard Facility for Solar Cell Calibration, which has been sponsored by MNRE, and we have taken up this challenge very positively. And I will tell you the success story today. So some of the glimpse of the facilities I mentioned about the solar cell fabrication characterization in our group. As you can see, this is the characterization. I mean, this is the wet texturing tools, or you can say wet benches at CSIR-NPL, housed in clean room for both acidic bases and organic chemicals. This is the processing facility which can be used for oxidation, nitridation of the silicon nitride coating, as well as phosphorus and boron diffusion from starting from 2-inch to 6-inch wafers. These are called diffusion and oxidation furnaces, which are housed in clean room complex. Then let me tell you about some basics of the solar cells, or solar photovoltaic cell. In fact, the photovoltaic cell basically works on the effect called photovoltaic effect, which was developed first observed by Edmund Becquerel, a scientist, almost 200 years in 1839. But the first practical device, that is solar cell, was based on the PV effect, was developed in 1954. And till 1973, there was not much global effort in the development of solar PV cell. But the application was mainly for the satellite application as a battery or so on and so forth. But after that, it was realized that this solar PV technology can be a very useful alternative source of renewable energy for terrestrial applications. So it is generally a semiconductor device based on PN junction, similar to a PN junction diode. And when the light is exposed on the devices, light is absorbed in the material, semiconductor material, generating electron hole pairs. These electron hole pairs are separated by the basically PN junction, or the electric field across the junction towards their respective electrode, and the photovoltage is generated. If the circuit is closed outside through a load, through a bulb, or through a fan, anything, then the electric current will be flowing, and therefore DC power will be generated. So the basic principle of a solar cell basically. And then you can see, I'm not going into detail basic, however, this is the equivalent circuit of a solar cell, which is assumed to be a constant current source, because it generates constant current under light exposure. This is the typical dark IV characteristics, which is just like a PN junction diode IV characteristics. And the red color is basically the IV characteristics of the solar cell under illumination of the light, because solar cell is a light sensitive device. And there are four basic parameters, which are called performance parameter of the device. Based on that, you decide whether your solar cell is a good device or bad device, how much power it is generating, etc., etc. Power conversion efficiency. So those parameters are the short circuit current, where the voltage is zero on the current axis, named as ISC. Then the open circuit voltage, where the current is zero, the circuit is open, that is the maximum voltage the solar cell can generate under illumination. Then from these two, curve, we have a perfect square fit, which decide the squareness of the IV curve and gives the fill factor or symmetric factor. And combination of these two, multiplication of fill factor, open circuit voltage, and short circuit current, gives you the maximum basically power, or you can find out the power conversion efficiency of the device by dividing this maximum power to the input power of light. So the maximum power is nothing but the Vm into Im, and Vm is the point on the IV curve where the power is voltage corresponding to maximum power, and Im is the current corresponding to the maximum power. And this is basically called the operating point of the device, of any photovoltaic device. So whenever we are designing a solar cell, as a researcher or a manufacturer, our main aim is to have these values as high as possible. That is, larger the short circuit current, larger the open circuit voltage, and larger the value of the fill factor, so that we have a maximum power and maximum power conversion efficiency from the device. Okay, so after introducing a little bit about the operation of the solar cell, basic solar cell, let me give you a brief idea about the entire PV value chain from raw material like silicon sand to the module manufacturing. So I can see that the polysilicon or the silicon chunks are then used to grow the silicon ingot. Then ingot is basically by CZ process, and then the wafering of this ingot is done. After that, solar cell fabrications are done by standard processes by solar cell manufacturing technology. And finally, these solar cells are connected into series or parallel combination to have in the form of modules. This is true for the monocrystalline silicon. As you can see, these wafers are pseudo square, but in the case of there are multicrystalline silicon wafer based technology also, is starting from silicon material, then silicon ingot is casted, then they are sized, segmenting is done. After that, wafering is done, solar cell fabrications are done, and then finally the modules are, or panels are made in order to have useful output power from the solar PV devices. And here is a bit more comprehensive PV value chain, starting from casting of the starting material, that is silicon chunk, to ingot, then sizing, then wafering, then cleaning of the wafers, diffusion to make a PN junction, finally anti-reflection coating, blue color you can say, the metallization of the contacts, top and bottom electrodes in the device, then interconnection of the devices to lamination of the solar cells or solar module, and finally testing of this. And most of the companies manufacturing of the solar cells are using this process line to manufacture the solar cells and module for deployment in the field. So till date, there are number of solar cell commercialized technologies are available based on silicon solar cells. The most one is the conventional screen printed or aluminum BSF based solar cell, which uses both mono as well as multi or polysilicon wafers. Then these, in the last 5-6 years, these new concepts have have dominated the production or manufacturing of the solar cell with aim to have higher efficiency of the devices, because these screen printed solar cell, aluminum BSF solar cell has got a saturation in terms of output power conversion efficiency. So this TOPCon means tunneling oxide passivated contact based solar silicon solar cell. Second one is passivated emitter rear contact based solar cell, passivated emitter rear textured based solar cells. Silicon solar cell with thin intrinsic layer, that is called HIT solar cell or sandwich solar cell, also interdigited back contact solar cells. Then combination of this IBC and HIT solar cells to demonstrate the highest lab level solar cell efficiency of 26.81 in the laboratory. And then considering all these devices for power conversion efficiency, if you look at in the market, then performance, depending on various technologies, the power conversion efficiency at cell level is ranging between 20 to 26%, depending on technologies. And on the other hand, module level efficiencies are between 18 to 23%. So after making the solar cells and module, next is to testing of the solar cell under the standard test conditions. And the standard test condition as per IEC standards are the intensity of the light should be, or irradiance should be 1000 watt per meter square. The spectrum of the light should be air mass 1.5 global. The cell temperature or the module temperature must be 25 degrees centigrade. And you should be very careful in measuring the area of the PV devices, because this area, a small error in the area will affect the solar cell current and therefore the power. These are the schematic. This is the schematic of the basically solar simulator in the laboratory or in the manufacturing plant. Mostly the solar simulators are used, as you can see some pictures of the solar simulators which are available at NPL. The simulated solar simulator having the light source, which is simulated so that they produce the one sun light intensity and a spectrum corresponding to the actual light we are getting from the sun in one sun condition, basically 1000 watt per meter square. So these are the pictures of the solar simulator measurements which are used in production line or in the laboratory. It generates IV characteristics as well as power. And the parameters I mentioned, like short circuit current, open circuit voltage, maximum power, maximum current, maximum voltage, fill factor, etc., and the power conversion efficiency. And based on the performance of the solar cells, they are sorted in different bins so that this will be used for this 100 watt module manufacturing, or 300 watt module manufacturing, or 500 module manufacturing, etc. So this is another example of that in production line. As you can see, solar cell having nowadays 2 bus bar. It is the old one, but now 5 bus bar, 6 bus bar, or even sometimes no bus bars. Technology is also available for solar cell manufacturing to have the higher power conversion efficiency and higher power to cost ratio. So after having the solar cells, testing, fabrication and testing, now time is to understand the typical solar PV system, what it consists of. So you can see that the solar cells are made, tested, then they are assembled into module like this, a combination of 60 or 70 cells in series or parallel, depending on what you want in terms of power output, current, and voltage. And these then solar PV modules are connected into arrays to make solar PV panel, and finally the long arrays of PV array, basically to have a practical solar plant, basically. But a solar PV system, if you see the solar cells are the basic building blocks, the starting point. And in addition to the solar PV array, you have a number of supporting electrical, mechanical, and components which basically support the operation of the solar PV system, in starting from battery, inverter, charge controller, generation meter, electricity meter, AC/DC isolator, mounting, and cabling, fuse box, and some tracking system is also used for some smaller system in order to track the sunlight throughout the day. Then what are the recent R&D efforts done by NPL? We have been contributing, R&D for industrial silicon photovoltaic, and have developed number of unit processes for the industrial solar cell. For example, in a couple of years back, we developed a process for black silicon solar cell. This actually is a purely chemical process and very fast process within a 30-second of time. This texturing of the silicon wafers is done not only the monocrystalline but multicrystalline. This process is called nanoscale texturization of silicon wafers. This is called process is called metal-assisted chemical etching. Here we are using silver as a metal for the catalyzed chemical etching of the silicon, and it has two-step basically electrolysis deposition of silver nanoparticles in the aqueous solution of silver nitrate and HF. And this is done for just 10 seconds, and followed by the nanotexturization of the silver nanoparticle deposited silicon wafers in the aqueous solution of hydrogen peroxide, hydrogen fluoride plus hydrogen peroxide solution for 15 to 30 seconds. And after removing the silver nanoparticle in the silver etchant, we have a silicon surface with surface having subvalent structures, having vertical dimension of about 500 nanometer and lateral dimension of about 2 to 300 nanometer. The beauty of this process is that within 50 to 30 seconds, this surface the process reduces the surface reflectance of the silicon wafers all the way from about 35% to less than 2% in the entire spectral range of interest for silicon solar cell, starting from 300 to 1100 nanometer, which is more than 30% lower than the planar silicon wafers, polysilicon wafers, as you can see over here. And it is also around 10 to 11% lower than the conventional micro texturing process, which is being used in the industry, and followed by, and also better than the texturing as well as silicon nitride combination, which reduces the reflection to around 5% in the entire spectral range. But this process, just by using a chemical etching solution in 30 seconds in a beaker, it does not require any sophisticated tool or gases hazardous gases, produces the surface reflectivity less than 2% in the broad spectral range. So this has got potential in the solar cell, and in order to test the potential, we made the solar cell in the laboratory just to see the proof of concept. And here the black silicon is basically the nano-textured silicon wafer, and this one is starting multicrystalline wafer. You can see the grain boundaries. We applied both on the monocrystalline as well as multicrystalline wafer. We could achieve more than 1.8% absolute enhancement in the in the efficiency, and 20% in the short circuit current density of the solar cell after the black incorporation of the black surface compared to the control cell without this nanotexturization. And um, uh, this performance was further tested by the reflectance map. As you can see, these nanotextured surfaces are still having less than 5% reflectance compared to the plasma surface, and the improvement in the current was confirmed by light beam induced current mapping in these solar cells. So this process has a lot of potential as an efficient and economic anti-reflection surface in the solar cell. And this nanotexturization process is versatile in a way that it can be equally effective for monocrystalline as well as multicrystalline wafers, which is usually not possible in case of by the conventional methods of texturization. So then next step was to check the suitability or feasibility of the lab developed process in the industrial line, for which we collaborated with Tata Power Solar System Bangalore. And then we took their basically multicrystalline silicon wafers of 156 by 156 millimeters, and then performed the nanotexturization in our laboratory. And you can see number of black silicon wafers processed in laboratory. We developed a single side texturing of this multicrystalline wafers. This is the back side, this is the front side, and it has not only reduces the reflection losses to a very low value, but also it has a wide acceptance to the incident light compared to the conventional textured and anti-reflection coated silicon wafers. So the basically it has omnidirectional light trapping property, and up to 60 degree of angle of incidence of the light. This a combination of nanotexturing is having the lowest solar weighted reflectance. So therefore, it has a omnidirectional light harvesting properties. And then after making this nanotexturization, we process the solar cell in the industrial manufacturing line of Tata Power Solar System on more than 100 samples, and we could achieve a maximum power conversion efficiency of 18.05%, which was with an average efficiency of 17.75% in a batch of 10 cells. And this was about 0.4 to 0.5% absolute higher than the conventional multicrystalline silicon wafers that was being processed in the production line in the same batch. Later on, we made the mini module also, and testing of this mini module 40 watt and 48 watt in our solar park at NPL, and so far there has been no problem in the degradation or the performance degradation of the module as well as performance of the module. So therefore, the developed process is fully compatible for industrial environment and can directly be adopted in this the developed process. That is what I wanted to tell the audience. And then another process, we developed PERC solar cell for passivation of the passivated emitter rear contact solar cell by applying the aluminum oxide of atomic layer deposition, and we could achieve a state-of-the-art surface recombination velocity less than 10 centimeter per second, and demonstrated the proof of concept of the PERC solar cell also in the laboratory in the industrial line. And in addition to that, our group is also actively working on some new solar cell concepts like perovskite solar cell, and has achieved a significant improvement in the power conversion efficiency. They have developed several organic materials in-house, as well as they have implemented these in organic solar cell to demonstrate around 9% efficiency in the direct as well as in the inverted structure. Recently, we have started working on the low cost polymer and silicon-based hybrid heterojunction solar cells, which is a futuristic technology, PV technology, because it reduces the fabrication cost very drastically, and we could achieve around 12%, more than 12.25% in the simplest device design on ice-cut thin solar-grade silicon wafers by effective surface microengineering. And next step, we actually wanted to develop the thin flexible silicon wafers and implemented the hybrid solar cell developments in this thin flexible silicon. So we developed a chemical process to achieve this less than 50 micron thin silicon wafers, as you can see here in the laboratory, because these such thin silicon wafers are not commercially available. So to test the concept, because as I said, that this technology, flexible silicon technology, is the future technology. So we should have all the parameters and the process parameters and processing of the solar cells optimized, so that once the thin silicon, flexible silicons are available, that can be those developed process can be directly implemented in the fabrication of flexible silicon solar cell in the industrial line or manufacturing line. So we developed this chemical process to achieve the less than 50 micron thin silicon wafers in the laboratory, and in the next step, we like you can see, we basically made the hybrid heterojunction solar cell by applying this process protocol. We started with 200 or 180 micron conventional silicon wafers, thin down to 50 micron. Then we perform one more point here. It is important to mention that when you have a flexible silicon of thickness, let's say 40 or 50 micron, then majority of the light will be transmitted. So you should have a very, and why thin flexible silicon is important, because it is said that around 40% of the cost of the solar cell is because of the material silicon itself. So if you reduce the silicon material compared to 180 micron to, let's say, 40 micron, then roughly you are reducing the cost of the material fourfold. So, but you should have an effective mechanism, effective scheme for the light trapping. And then we worked on this actually very 2-3 processes of effective light trapping in the for thin flexible silicon. In the first step, we applied the micro texturing, random micro texturing by KOH process, alkaline KOH, potassium hydroxide texturing, to minimize the reflection losses, and then met the solar cell by this scheme. The device is very simple. You have a P.PSS, conjugate organic polymer, which act as a whole transport layer. Then we have a thin oxide layer, then flexible silicon, bottom contact by indium gallium, and top contact by silver. We could demonstrate the 10.4% power conversion efficiency, which is at par with the state-of-the-art flexible P.PSS silicon solar cell in the world for such a thin silicon wafers in the simplest device structure. In the next is this is the publication that we got in Journal of Materials Chemistry C very recently, last year basically. And then we applied silicon nanowires. Also, we had a lot of work on silicon nanowires on this flexible silicon wafers to test the light trapping. Here also we could achieve more than 9% efficiency. Another publication, sustainable energy and fuels. And another concept of light trapping, basic idea was to test a different light trapping scheme for and test which one is better. So we also applied the plasmonic effect of silicon nanoparticles on such flexible silicon wafers, and could demonstrate successfully the flexible hybrid silicon solar cells, and published in ACS Applied Nanomaterials a few months back. And we have also collaborated with IIT Delhi Department of Energy Science and Engineering for development of the HIT-based solar cell. This project is funded by DST Nanomissions, and we have achieved about 18% efficiency till date. Our target is to have 20% efficiency, and we will be able to achieve in next 2 years. So the problem is that after having a brief introduction to all the efforts, research efforts done by CSIR-NPL in the solar photovoltaic and other activities, here I would like to mention then why there is so much buzz about the solar photovoltaics, not only in India but around the world. The primary cause, I believe, is, and everybody believes that the fossil fuels, conventional energy sources are depleting continuously. They have a fixed reservoirs. So we have alarming energy crisis. And not only that alarming energy crisis, but excess use of fossil fuels are also causing environmental issues, right? So, but at the same time, if you look at the solar energy, we have um, huge source of free and everlasting energy and in almost carbon free medium. As you can see, sun radiation onto the earth corresponds to 120,000 terawatt, and the total human energy need today in a day is only about 13 terawatt. So we are receiving almost 10,000 times energy free of cost, and which is going to last forever from the sun every day. What we have to do, we have to have an effective and efficient mechanism for harvesting this free of cost sun energy to convert into electrical energy, electricity to meet our practical needs, daily needs. So the solar energy is the only kind of energy that can solve the Earth's energy problems alone. As such, the capacity of the solar energy is this way. So that is why there is a lot of buzz on the solar photovoltaics. So we need to have efficient and good solar cells or PV cells. And there is a study which says that if we have 6 areas of 340 kilometers by 340 kilometers, and then we need only PV cells of only 15% efficiency to get around 20 terawatt of energy generated from the solar energy through these PV cells. So 15% device laid down on 6 areas of 340 kilometers by 330 kilometers in the world can meet our energy demand. So that is the huge potential of the solar energy, and photovoltaics can play a big role in this energy challenge. But the next question is why the silicon wafer based photovoltaic devices are dominating the PV market or PV device market. In the current PV market, we have a more than 90% domination by the silicon wafer based solar PV devices in world basically. There is plenty of reason to answer why only silicon based. Reason being that silicon has more than 60 years of manufacturing experience. As I mentioned, that it started, getting in attention from 70 onwards, even much before. And we have a huge technology base for the silicon photovoltaic. Why? Because silicon is the most second abundant material as a raw material we have. Then the processes, device design, all are backed and driven by the development of microelectronic industry. All the processes, all the equipments which are developed by for the microelectronic industry can easily be incorporated, adopted for the manufacturing of the solar cells in the industry. So it is completely backed, and the silicon is one of the most studied material. All the material properties are known. We have extensive track record in terms of performance, lifetime, and reliability of the PV cells based on silicon wafers, and the highest performance so far, both at cell level as well as module level of silicon wafer technology. Therefore, the PV industry is driven by the silicon wafer-based solar cell. So now coming to why solar PV is so important for India. But before that, we will discuss a little bit briefly about the energy scenario of the country and what is the potential of the basically PV in the renewable energy technology goal. So if you look at the India energy challenge, this can be understood in this five, manners. First, if you look at in demand, then in next 10 years, it is expected that India's electricity requirement is going to grow 2 to 3 times, right, compared to the present demand. We have a large number of thermal plants which need to be renovated and replaced because they are old, which are based on coal basically. Thermal plants are basically based on coal. and these plants have lower plant load factors, PLFs. So this is one issue. Then we have basically because of large amount of thermal plants and oils uses, that the climate change is a major issue, which is driving the basically renewable energy, mission around the world and in the country as well. And we have basically India has committed in the summit to produce 50% of electricity by 2030 from non-fossil fuels, that is RE sources, the renewable energy sources. And it has a target to achieve the net zero emissions by 2070 in the country. But at the same time, uh, demand and supply gap there in the shortage, because still we have a certain shortage of energy production, inefficient and inadequate distribution of and transmission or delivery system through in the country, though there have been a lot of improvements, significant improvement through smart system in the last few years. And if you scrutinize this critically, you will find that still lots of people in the remote areas are without access to electricity. So, and the most important here, or the most critical one, is the energy security. Every country wants to have self-sustainable energy security, because anytime anything can happen. You can see the recent wars between Russia, Ukraine, Israel, Lebanon, and so on and so forth, which impact the the international market in terms of if you are heavily dependent on imports of oils, etc. And India is dependent on oil imports for more than 70% of its demand even today. So here is the India's energy ecosystem. We are the most populous country, more than 1.4 billion, about 18% of the total population of the world. We are the fourth largest economy by GDP, and we are the third highest in energy consumption, and the third highest in net energy importer, as I mentioned in the previous slide. And we are third highest in energy production as well. But still that energy is not meeting our entire energy demand, ever increasing energy demand. Why? Because average energy consumption growth has been 6% per annum, and till date. It was about 7.3% in 2003, and it is projected to increase further with the further development, advancement, and technological developments in the country, commercialization, and so industry growth as well. So the GDP growth rate is expected to be in the range of 7 to 10%. It is projected, though yesterday or today only we heard that the this quarter GDP is 5.54%, but it's still very large, and we are have a positive this that our this growth will be between 7 to 10% in the coming years. So keeping all these things, we should have a strong mechanism for securing energy sources. And the supplies is of very, very strategic importance for the growth of the country, for the growth of India. Therefore, this needs to be done in a sustainable manner, largely through indigenous sources. As I mentioned, if we are heavily dependent on imports, these imports can be affected badly by any international scenario. Example is Russia, Ukraine war, or any other in the world. So, though, what is so special about solar for India, or solar PV for India? You can understand with this solar map of the country in the India. Actually, we are very fortunate to have more than 300 sunny days in the country. We are solar rich. We are receiving in most part of the country area solar radiation of about 4 to 7 kilowatt hour per square per meter per day. And the total potential of the solar capacity, basically potential of the country, is calculated to be estimated to be 748 gigawatt, which can meet the growing energy demands and cover deficit areas, such an area where we do not have a rich solar mapping that can be also fulfilled by this strong regions, and can substantially reduce carbon footprint for lighting and power generation. Therefore, we have a cleaner energy, and it can also provide access and empowerment in it at grassroots level. If we have a strong solar PV, electricity conversion mechanism, Here is basically solar resource mass for India to India solar in direct mode and global mode. And it has been NREL, National Renewable Energy Laboratory, has mapped this country solar potential, and it is calculated to be 748 gigawatt. Total production is possible, which can meet our total energy demand. Of course. So therefore, solar photovoltaic has been, projected a realistic and promising renewable energy technology. Considering this, the country launched a national solar mission in January 2010. It is one of world's largest renewable energy expansion program, in which we have, target of 500 gigawatt installation by 2030 in the renewable energy sector, and which is dominated by the solar PV, where we have a target of 280 gigawatt installation by 2030, alone by solar photovoltaic. So solar photovoltaic is basically green, sustainable, and economic, and therefore it has a large potential. And you'll be happy to know that we are on right track. And as per the latest MNRE report, by 30th September 2024, we have achieved around 91 gigawatt solar photovoltaic installation in the country. India is a signatory of the International Solar Alliance, consisting of 123 countries, and most being sunshine countries. It was done in 2005 by Honorable Prime Minister, Government of India, and French President. And India is basically founder member of ISA. We have a headquarter of ISA in, basically in Gwalpahari, nice. So you can see, you can compare the role of solar photovoltaic in the entire renewable energy progress scenario, and it is dominating in the complete total 201 gigawatt installation has been achieved of all the renewable energy sector, and you can see that almost 50% is by the solar photovoltaic only. And the next projection pipeline capacity in gigawatt is also quite high. You can see 102 gigawatt is projected, are already in the pipeline. So the solar photovoltaic is dominating in the entire RE sector for all application. As you can see, you can compare in this table, and it is solar power cumulative is about 90.76. This is the 30th September data, and in last 2 months it has crossed, I think, 92 gigawatt installation in the country. It consists of ground mounted solar plant majorly, and then the grid connected solar rooftop are also there. The hybrid projects like solar, wind, etc., where solar component is 2.63 gigawatt, and off-grid solar systems are also up about 3.78 gigawatts. Here is the year-wise progress installation in the cumulative installation of the solar PV power plants. As you can see that it is increasing drastically. Earlier it was in March 16, it was 3 gigawatt, then 5.6 gigawatt, then 9.5 gigawatt. There was a slight, down in the 19 and 20 because of because of the COVID pandemic, and thereafter it has again caught the pace, and in 2022 it was about 13 gigawatt, and same in the 2023, and till date, I mean September into 2024, we have crossed 15 gigawatt capacity of installation, solar PV installation in the country. And the solar park capacity has been doubled from 20 gigawatt to 40 gigawatt. As you can see there, these are some list of the largest solar park installed, built up in the country, and the highest one is 2.245 gigawatt capacity in Rajasthan, Jodhpur, which is called Wadla Solar Park, and similarly there are many more. So these are actually all these data. You see what are the driving force. So the major drivers for solar photovoltaic, growth or success in India is basically listed over here. They are able to meet the growing energy needs. As I mentioned, I explained in the previous some slides. They can replace the fossil fuels. They can reduce the dependency on oil or coal imports, so we can achieve energy security in self-sustained manner. They can reduce the environmental impacts like greenhouse emission gases, etc., can be reduced. we have energy conservation. They can also help in peak load saving. The government has taken numerous measures and several policies and schemes to promote the solar photovoltaic adoption in the country. They have encouraging and supportive policies for domestic production for the manufacturing company, be it solar cell manufacturing or the module manufacturing or any other related components for the solar PV system. Then awareness and larger acceptance and support by the common people, which is the most important component in the success of any industry, any policy. So India at current is the fourth largest PV installed capacity worldwide, followed by Japan. The top one is China, second one is USA, third one is Japan, and India is fourth, followed by basically, and the next one is Germany. So it is not that easy. There were several challenges, but despite challenges around grid integration, energy storage, Indian government initiative have supported widespread solar adoption, as I mentioned here. And some of the schemes initiated by the government of India are listed over here. They have production linked incentive scheme, and they have effective solar energy corporation India auctions and competitive bidding. They have PM Kisan Urja Suraksha एवं उत्थान महाअभियान like PM Kusum for farmers, and then we have a PM Surya Ghar in nowadays in the common people for the rooftop installation of up to 3 kilowatt of the solar PV energy. So solar PV technology offers long-term sustainable solution that I think I was able to brief you, give you an idea about what is the potential of the solar PV installation in the country. Hello. Yes, sir. I think I'm audible. There was.
Yes, sir. You are very well audible.
Okay. Thank you. Thank you so much.
Thank you very much, sir. Thank you.
Okay. So next, if you look at all these data so far I have presented, and there is one, we have everything rosy, everything going good. And these data are basically the testimony of the grand success of the National Solar Mission in the country towards achieving the net zero emissions and the production of the 50% of electricity by non-fossil fuels are through renewable energy sources, and also towards the energy security in the self-sustained manner. But these are all the positive side. There is a little gray section also, and in this huge deployment of the PV plants in the country, which need to be taken care very, very seriously, because if this is there, then it is threatening to the success of the national solar mission in the country. And why I am saying this, you can see that here this curve explains you why what, and it tells you the degradation rate of the solar PV modules installed in the field. If we have a yearly degradation of 0.8%, then the expected life of the solar module is about 25 years. As you can see, if we have a degradation of 0.65% yearly, then we can expect the lifetime of the solar PV module in the field about 30%. So this is the data, and most of the manufacturer company are the installation or the power company which is providing the solution, installing the plants. They claim a minimum life of about 25% for 80% of peak power. So, however, a recent study, or maybe just a study done by jointly by NCPRE, IIT Bombay, and MNRE, NICE, National Institute of Solar Energy, on some of the plants modules installed 10 years back, what they found that the average degradation rate of these modules was 2.07% per year. And they tested it on number of modules of 750, more than 750, and median was 1.96% a year. So if you consider this, then more than 2% of degradation rate, annual degradation rate of these modules, then their lifetime will be less than 10 years only. Hardly 10 to 15 years they can survive, as compared to the guaranteed warranted 25 years of lifetime. And there could be these modules are actually failing. These are certain examples. So such a fast degradation, failure of the modules and will not cause a huge financial loss, because you have paid for 25 years, but they are failing in 10 years or maybe 15 years. So you have a huge financial loss, but also you will create a huge solar waste, which will be recycling or disposing of such huge solar waste will be a nightmare. So that it will create a great environmental issues also. So we had a number of brainstorming meetings among all the stakeholders at NPL, involving MNRE, BIS, NEBL, CBCB, and industries, manufacture, research laboratories, and so on. And then we found a consensus that why this, what could be the reason for the fast degradation of the PV modules in the country. What we found that we are heavily dependent on import of cells and modules. Still, of course, module manufacturing capacity is around 60 gigawatt today, as I found in some data. But are we able to produce these cells in the country itself? We don't have cell manufacturing capacity at such a low level. So we are importing the cells from some other countries and making them into modules. And this is one that we are heavily dependent on imports of cells as well as modules also. And some companies are exporting also. I'm not saying that with this one, but still we have a large import. Modules are tested as per European conditions. All the test conditions, 61 IEC 61215 or BIS, basically IS 14286, are these test conditions are as per the European, protocols, European conditions, where the weather conditions are completely different than our extreme, condition. Indian climatic conditions are different. We have extreme temperature, we have extreme humidity, dust, wind, and so on and so forth. So those, module tested under the European test condition under limited condition may not, be, perfect in our environmental condition when deployed in the field. There may be possibility that module test labs are, of course, we have a limited, because we have a huge target of, installation of about 15 to 20 gigawatt per year, and lab tests are not that sufficient enough to test all the, modules, and therefore results are questionable. Tested modules fail in the field, and I mentioned that this is creating a huge environmental effect. And since the modules are getting installed today, but after maybe 10 years or 15 years, if they are failing prematurely, then there will be huge solar waste, electronic waste, and recycling of these waste will be very, very difficult and will cause a huge environmental impact as well as social impact. Nevertheless, this was one issue. Another issue is that the electrical data sheet, which are provided by the manufacturing of the modules, as you can see, some of the examples are here, like maximum power of 335 watt, current voltage, and so on and so forth. Similarly, another model has 200 watt, and these are all as per the stated guidelines. They are tested under STC 1000 watt per meter square, 25 degrees centigrade, and a spectrum of N1.5. So based on that, the module manufacturer, they give a product warranty of 10 years against any mechanical and other failures. Performance warranty, power output in terms of power output, 90% power output to up to 10 years, and 80% power output, stable power output up to 25 years. So this is the standard. But is it possible to trust the PV module electrical data sheet blindly? If that is so, why there is so much differences or degradation in the performance of the devices? Therefore, NMI like NPL has got its role to ensure measurement quality, traceability chain, and international equivalence. I'm so slowly moving the importance of the metrology, PV metrology or traceability chain. And I would like to sensitize you one more thing, one more problem, what economical impact it can have due to the measurement uncertainty. So as I mentioned, sorry, the graph is not so that clear, but this tells you that the growth of the PV installation in the country year by year. And as I mentioned in one table, that we have around on an average 15 gigawatt installation per year. So there is one example, even 1% uncertainty in performance or efficiency power measurements may lead to a revenue loss of about 2,000 crores for capacity of 100 gigawatt installation if we consider 20 rupees per peak watt of the module cost. This is very simple calculation. You just multiply 100 gigawatt by 20 rupees, and the total cost, you take 1%, it is coming 2,000 crores. Another example I'll try to explain it to what would be the measurement uncertainty on economic impact. So the financial uncertainty in the solar plant can be calculated by annual installation into the price of the power and to the uncertainty. So the financial uncertainty, let us suppose 15 gigawatt per year installation into 2 rupees per watt of the tariff that presently companies are bidding. And if there is 1% uncertainty in the measurement of the power of the module, then it will result into 300 million rupees per year, 30 crore rupees per year. There is no certainty whether of this amount because of the uncertainty in the measurement. You have paid for, let's say, 15 gigawatt, but you may not be getting 15 gigawatt because of the uncertainty in the measurements. So a measurement uncertainty of 1% leads to a financial uncertainty of 300 or 30 crore only due to operational loss. So there is a demand for high accuracy solar cell calibrations in the country in order to ensure that the PV products are accurate as per the data provided or given. So therefore, solar and another thing I must tell you that solar parks are financed from banks who add the financial uncertainty arising from the measurement uncertainty to the total amount to be financed, right? So they will cost more considering this financial uncertainty. Thus, a lower uncertainty leads to a competitive advantage. If you know the uncertainty is lower, then the costing will also be accurate, and therefore the uncertainty in the economic parts will be reduced. That is how the PV metrology and traceability chain is very, very important. So try to understand with this what we found that there is some issue in national traceability chain which is probably not complete or partial compliance is there because of which there is a failure of the modules as well as the uncertainty in the estimation of the power and performance. We have a dependency, huge dependency on other NMIs. Our traceability is missing because so far we do not have, this is the traceability chain, I would say. We have a primary standard at NPL, then SI, and then test labs are basically calibrated against the primary at NPL, being NMI, and then the PV industry is basically using that traceability chain or uncertainty measurements for the calibration of their product, PV cells and solar simulator, etc. So we should have NPL industry linkage traceability pyramid complete without any breakage in between. So so far, I think we believe that there no such PV metrology primary facility was available in India to have unbroken chain of traceability. We were mostly dependent on foreign countries for calibration of reference cells, and hence solar simulator. In view of the national solar mission success, such facility was of utmost importance. And considering this, we proposed the establishment of primary reference solar cell calibration facility at NPL so that we can fill the gap and provide the unbroken chain of traceability of measurements of photovoltaic cell performance all the way from SI unit to the PV industry or the customer user. Before this, of course, but we had to send our reference cells for calibration to the PTB or NREL USA or IST Japan or some other country to get the cells calibrated, right? That also, caused the foreign exchange as well as time. So what is a PV metrology or calibration chain in PV product value chain? So traceable calibration, try to understand. Here is the flow chart, dictating the basically the metrology chain or traceability chain of the PV product, starting from primary reference to the PV module, which is being used by the customer. And traceable calibration and testing of PV devices is very basis of assuring the worldwide comparability of electrical parameters of PV products in terms of efficiency and power. So unless until we have unbroken chain of uncertainty measurements in the PV product performance, it is not possible to compare our product with another product or assure the international equivalence in the global market. So the calibration chain links the industrial production via calibration and testing labs, as I mentioned in the previous slide through the pyramid. This calibration chain links the industrial production via calibration and testing labs to NMI and hence to the SI units. So the most crucial measure for the PV traceability is the short circuit current under the standard testing condition, which is denoted by ISTC, I for current, STC for standard test condition. Since this ISTC or the short circuit current directly correlates to the irradiance conditions defined by the IEC 60903 standard. So in this chain, basically we have a cryogenic radiometer which is calibrating the giving the calibrated flux or power which has uncertainty of less than 0.1%. Against that, a photodetector, standard detector is calibrated with an expanded uncertainty of 0.1%. Against this photodetector, the primary reference solar cell calibration, is calibrated, which gives you the spectral response and ISTC with an uncertainty of about 0.5%. And against this reference cell, our solar simulator, our IV characteristics, solar simulators are calibrated, which produces the IV characteristics, and these solar simulators are basically used by all the solar cell manufacturer and module manufacturer to test the performance of the cells and modules, and finally the power to provide the customer. So finally, the PV modules are tested, and if this unbroken chain is maintained, then we say that the performance, whatever we are there, have the known uncertainty, and therefore we can estimate it correctly, and it should be as low as possible. Try to understand a better way here what is the traceability in the entire PV product value chain, starting from SI units. This is the top one. Then the NMIs are World Photovoltaic Scale Laboratories, are calibration lab like PTB Germany, NPL India, AIST Japan, NREL. These are basically the World Photovoltaic Scale Laboratories. And we have a primary reference solar cells, which can have a calibration uncertainty of 0.5%. Here, the calibration value is basically ISTC. And this, as per IEC 60904 standard, the standard test conditions I have mentioned again and again. Irradiance would be 1000 watt per meter square. Spectrum and air mass 1.5 global. Temperature of the cell or device under test would be 25 degrees centigrade. So this is the reference cell which is calibrated in the NMI, and then against this reference solar cell, the golden reference cell or modules are calibrated with a little higher uncertainty. The testing, these are basically calibration and testing laboratories which are fulfilling the ISO IEC 17025. They have this facility, and they have the calibration uncertainty of about 1.3% or lower. And then finally, we have a PV cell and module calibration against this golden reference cell and module, or you can say the working standard. These are calibrated, which are kept by the manufacturer, and they have the uncertainty of about 3% in the short circuit current density, short circuit current or photo current, you can say. And finally, this power maximum at STC is given to customers and users. So here ISTC is basically short circuit current, which is used for setting the irradiance level of the solar simulator. If your ISTC is not correct, then your intensity or irradiance of the solar simulator will be not correct, and therefore you can, have the power measurements with larger uncertainty, lower or higher. And this spectral responsivity at STC, basically standard test condition, is used for the determination of the spectral mismatch correction factor, whether the solar simulator spectrum AM 1.5 or not. That is also important to note in the calibration chain. So a little bit, background about. I'll quickly go through what how to determine this photocurrent and what is the role of a spectral response. You can see here this we have a spectral irradiance corresponding to AM 1.5 as per the IEC 60904 document, and we have defined a spectrum. So we know that is spectrum, and but we should have a spectral response of the solar cell of the device which is being used as a calibration, chain. And depending on knowing the spectral response of the solar cell accurately, absolutely, we can use this formula to find out the photocurrent with associated uncertainty in the determination of the photocurrent. So the SR calibration or spectral response calibration is also very, very important, as I mentioned in the previous slide, to determine the ISTC, but also because it is used for the calculation of the spectral mismatch correction factor for PV calibration using a solar simulator. This is also defined in IEC 60904-7. We should have this spectral response in order to correct the spectrum of the solar simulator. So that it is exactly AM 1.5 global, not AM 0 or AM 2 or something else. And for research purpose also, spectral response provides a measure of recombination and other processes occurring inside the semiconductor or cell material system. It can also be used to assess the quality of the solar cell, in which region more recombination or more losses are there, so that you can improve your process to remove those problems, issues, and have efficient solar cell devices. This spectral response is also used as a reference for the differential spectral responsivity system or spectral response facilities for calibration. And this spectral response, as I mentioned in the previous slide, can be used to determine the ISTC, determine the short circuit current at standard test condition out of absolute spectral irradiance spectral responsivity. And these all guidelines are defined by the IEC 60904 document. So there are three most commonly methods used for the calibration of the PV devices internationally. One is the natural sunlight, this is also called outdoor method, which is basically used by the NREL USA. And I will compare these three methods here in the bottom. Another one is based on solar simulator, pulse or steady state. And the third one is the spectral method, as I mentioned about the spectral response, which is basically such as the differential spectral responsivity, DSR method, which is developed by PTV Germany. So here you can see in the picture. So these three methods are compared. Outdoor calibration is of course direct. It has total global radiation, but the problem is that it required appropriate and stable weather conditions while the calibration of the device, which is very difficult to maintain, control the weather condition outside. So we may have a very limited days where we can have a control outdoor, radiation condition for the calibration of the devices. This is the one limitation. And here also spectral mismatch correction is required. So we should have a spectral mismatch data. In the solar simulator like this, of course, it has a good reproducibility. Independent of place, location, and time, it can be done in the laboratory, not outside. It can handle large cells, modules, and fast measurements. But here also you need to have a correct spectral, mismatch for the accuracy of the spectrum. On the other hand, the differential spectral response method, which I am going to talk about further, and our method is also based on this, concept principle. It is absolute method. It has all the advantages as solar simulator. It is has a good reproducibility, independent of place, location, time, and so on and so forth. Can be done in the laboratory condition environment. Absolute method. It is an absolute method without a spectral mismatch. It does not require any spectral correction. However, it can handle cells up to 15 by 15 centimeters square only, and it is a slow measurement. I will mention that this method requires 2 days of the complete measurement followed by 1 day of calculation of the data to arrive with uncertainty and so on. So the differential spectral response method as defined by IC 60904 is a two-beam method in which your photovoltaic device or solar cell or reference solar cell is illuminated by a monochromatic light of certain intensity of a particular lambda. Simultaneously, the continuous bias light, white light, consisting of all wavelengths are also illuminated. And we have it is based on locking technique. The monochromatic light signal generated to corresponding to monochromatic light uh, pulses are measured by the lock-in, and the current generated by white light is by multimeter here like that. And the spectral, as you can see in the plot corresponding to radiance, we have a monochromatic plus bias radiation, both the blue and this, and we have only bias radiation. So as a result, you can find out the differential spectral responsibility corresponding to bias radiation of EB in terms of delta I corresponding to monochromatic light in presence of bias versus the illumination of the monochromatic light. And since the delta E, that is the illumination, monochromatic light intensity is much lower than the bias light, you can have in di by dou over E to get the spectral response of the test. So after having a brief idea about the basic principle of this calibration method and importance of traceability of measurements of the PV devices, in view of the huge installation and ambitious target of solar PV installation in the country. Then, as I mentioned, that we proposed to establish this laser-based differential spectral response with a calibration facility for the calibration of the solar cell, reference solar cell at the CSIR-NPL to MNRE, and MNRE was kind enough to fund this project. So the aim of the project was establishment of primary standard facility for solar cell calibration with measurement uncertainty of 0.35% in the short circuit current at confidence level of 95%, and which was targeted to be the lowest in the world among the world photovoltaic laboratory scale, and its dissemination in the country. And its importance is very, very big because it can provide you accurate estimation of the PV product value to minimize the financial implications across the PP value chain, as I explained in some of our earlier slides. And uncertainty, what we targeted for 20 by 20 millimeter square solar cell, which are the most useful reference solar cell at confidence level of 2, was 0.3%. On the other hand, for the cell of industrial solar cells of 156 by 156 size, it was targeted to be 0.6%. And then for that implementation of this project, we had a scientific cooperation agreement with PTB Germany, which is NMI of the Germany, and it was signed on October 5th in 2018. And here is the schematic of the facility that we had proposed to develop and install at CSIR-NPL. For the sake of simplicity, I will not go into detail of the technical part, but this facility has laser source instead of classical xenon lamp source, and it can produce the light, monochromatic light in the very wide spectrum range, starting from 230 nanometer to all the way to 4,000 nanometer, covering all sort of solar cells to be calibrated by this facility. So it has three components: laser as a light source, then optical components, monochromator, etc., to reduce the bandwidth and guide the laser beam on the device under test. I'll show you the actual picture, and then recording and the electronic components, etc. So what is the advantage of this laser DSR versus the classical DSR? It is a next generation DSR, better than compared to PTV. It has a long spectral range and therefore applicable for other solar cell. I mentioned that it has, from 230 nanometer to 4000 nanometer spectral range. It has a narrower band width of spectral wavelength. Therefore, it can provide you better uniformity and lower uncertainty because of the narrow bandwidth in the light source, better signal to noise ratio. So higher power of monochromatic light on the measurements plane for device under test for all wavelengths, the lower wavelength or the higher wavelength, which is difficult to get in the classical xenon based lamp based DSR system. It has a larger area uniformity. It is basically due to the properties of the laser, which you can illuminate the larger cell. Like that's why we are able to do the calibration of the 156 by 156 millimeter square industrial size solar cell with lower uncertainty. So these are the advantages, and this development was started and in year 2022. 2022, we visited myself and my colleague Dr. Pratap, who is basically PI of this project and co-PI, visited PTV Germany to have a knowledge transfer, to take part in the development of this facility, as well as gets hands-on training on the each and every component, be it optical, mechanical, software, control, laser, and alignment, calibration of reference solar cells, fundamental measurements and calculation, everything, all aspects we went through and learned. And this is basically the picture that this is the facility at the site in PTV. And then our better view, you can see this is the actual laser DSR facility installed, established at PTV for NPL, and we were involved in the development at their site. And the next, after the development and assembling of the facility, the next task was to test the measurement capability of the facility, or assessment of LDSR system performance before it is shipped to the CSIR-NPL for installation. So our target was assessment of desired performance of the facility, pre-shipment of the system to CSIR-NPL with a targeted uncertainty of 0.35% in the short circuit current at standard test condition with a confidence level of 92%. And for that, we selected two world photovoltaic scales reference solar cells named as RS82, which is a nonlinear crystalline silicon solar cell, and 0702 to 2016, which is a linear solar cell. As you can see their pictures, these were the calibration object. We performed the standard measurement procedures to measure the DSR of the WPBS solar cells as per the set procedure by the IEC standards. And these are the absolute differential spectral responsibility of the two devices with associated uncertainty on the top. And as you can see that the cell which was nonlinear basically had a nonlinearity of 4.8%, and again proved that it is nonlinear. On the other hand, the other device 70 to 2016 could have nonlinearity of only 0.2%. Therefore, it is considered to be linear. So this spectral response are basically absolute spectral response of the devices generated under different white bias light. This facility has got the capability to measure the spectral response under different bias light in order to assess the linearity of the device, because there may be some reference solar cell which may not be, producing the problems due to the defects. Some defects are light sensitive. They can be activated only when we have a white bias light on the device. So that is why this technique, this DSR facility is equipped with that, so that we can have a linear testing of the linearity of the device as well.
We'll talk to her later.
So I'm not going to detail the after the measurement, the spectral response are basically determined. The measurement is cosine. Cosine is basically the signal of the device corresponding to the monochromatic light, as well as the reference, and then they are calibrated against the reference photodiode. There are certain number of corrections which are incorporated in the devices. You can see the amplification factor in the transimpedance amplifier, lock-in amplifier, non-uniformity, distance, shadowing, temperature, wavelength, bandwidth. But these are the corrections which we can estimate, but there are certain things which are contributing to uncertainty, but we cannot estimate them. So we are incorporating them as a uncertainty component, and there are more than 20 components which are taken into account to calculate mathematically detail through a Monte Carlo approach. That's why it takes 1 day, complete 20 hours almost, to calculate the uncertainty in the spectral response and the ISTC. So finally, after incorporating all these uncertainty component, we have the uncertainty in the ISTC value and spectral response of the device, that is the reference solar cells. So finally, what happened? We performed the assessment of the device, then we perform the intercomparison also, because it is not that I measure, you measure, and we agree together, but we should have an intercomparison among the World Photovoltaic Scale Laboratories, and there are four World PVS, basically WPPS laboratories: NREL USA, PTV, AIST, and TIPS China also. So we took these two cells for the intercomparison, and here is the intercomparison mechanism. The calibration value was ISTC basically. First, those two cells were calibrated by PTV, then it was sent to NREL, then the NREL calibrated and share the data to PTV. PTV again measured the, calibrated the devices. It was again calibrated by NPL India facility at PTV side, then again it was calibrated by PTV. So here are the calibration value chain, and I'll not go into detail of the calibration method and so on so forth. I have already explained of the three methods. NREL uses outdoor method, PTB DSR, and NPL India method is laser DSR method. Finally, what we found, the individual calibration values were normalized to the weighted mean, as you can see in the plot for the two reference solar cell. And as per ISO 17043, if the absolute EM numbers of the individual calibration values with respect to the weighted mean of the calibration values are less than 1, then it is says the measurements are considered consistent within the stated uncertainty. And the uncertainty we calculated was 0.35%. And since the IN numbers are, for these two reference solar cell, as you can see in this plot, is less than 1 is here, quite less than 1. Therefore, the stated uncertainties are considered consistent as per the ISO 17043. Therefore, we were able to demonstrate the achievement of system performance with target measurement uncertainty in the photovoltaic reference solar cell of 0.35% at confidence level of 2 in the ISTC. And this is the current state of the art measurement among the 4 established world photovoltaic scale laboratories in the world in terms of the lowest uncertainty measurement in the short circuit current at standard test conditions. The next step was, I will take another maybe 5 minutes, sir. Okay. Hello. Hello.
Yes, sir. Yes, sir.
Another 5 minutes, sir. Is it okay?
Please continue. Please, no problem, sir. You have the sufficient time.
Okay. Thank you.
Thank you very much, sir.
Yeah. So after developing and testing the facility at PTV Germany, then the next step was to bring shift the facility at CSIR-NPL. But before that, we should have a site preparation. There are certain stringent requirement as per the IEC standard. So we had this PV photovoltaic metrology room ready in our campus in the solar energy complex of dimensions 10 meter by 10 meter and class 10,000. This is the picture of the site before modification of the condition, and the condition was 20 degrees centigrade per plus minus 2 degree and relative humidity of 50 degree plus minus 10%. However, the required condition as per the IEC was 25 degrees centigrade per plus minus 1 room temperature and relative humidity of 45 plus minus 5%. So then this is the three-dimensional view of the room as well as the facility in the CAD design model. The facility actually look like this. So we then modified the room. We got the room modified as per the required condition. The site was completely renovated, modified as per this requirement of the facility. And the facility after the modification, the room site basically of the facility after the modification look like this. We had to have a complete, black, surfaces around. I mean, everywhere in the room, be it wall, floor, roof, etc., so that we should have minimum stray light, affecting the measurements. And of course, this uncertainty where we are talking about even 0.01% uncertainty is very, very crucial. Therefore, we had to do this very, very stringently. And then we, the facility was packed and shipped, and then we started assembling, installation of the laser component, optical component, etc. Some basic level were done by ourselves. Certain critical, components were, done by the German team. They visited, for example, this XY stage, which was very, very important and very has to be assembled very precisely. So these people also visited to help us in the installation or assembling of the facility. And after, these are some pictures of the, during the installation of the facility. And then finally this facility was, installed completely, physically. All the, electrical, mechanical, electronic and communication, software control, everything was, installed, tested, communicated, and we did the measurements for just maybe a better feeling. I will try to play a, video of the facility in operation if it is, visible to you. I hope. So is this video visible?
Yes, sir, visible.
Okay, great. So this is the facility in operation. This is the National Primary Standard Facility based on laser DSR method used for the calibration of the primary reference solar cell at CSIR-NPL. Okay, good. So this is the status of the facility at NPL. We are almost ready, for this. Then we also, this next task was basically to test the assessment, perform the assessment of the, facility or the calibration measurement capability of the facility at after installation of the facility at CSIR-NPL. And we did that. We selected two WPPS reference solar cell named at 10/20/19 and 9/20/19. These are just the reference number. And we performed this absolute differential spectral responsibility measurement and calculated. This is actually for the 9/20/19. And then we performed the detailed spectral response measurement and calculated the spectral absolute spectral response as well as the ISTC with associated uncertainty. And we found about 0.35%. In fact, it's a little lower than that, but to be safe, we declare it 0.35% here. And then we perform the intercomparison with the PTB Germany also with their facility, with their DSR facility. And here are the comparison, as you can see. And this, the calculation of the EN value as per ISO 17043, that is the, ratio of the individual calibration values normalized to the weighted mean, and EN value must be less than 1%. These are the EN values which are quite lower compared to 1. Therefore, the stated uncertainty 0.35% is consistent, and the measurements are consistent within the stated uncertainty. Therefore, it is the declaration and the achievement of the stated uncertainty in the short circuit current density of the world photovoltaic reference solar cell with the lowest uncertainty. This is basically the primary standard facility is now established, and accomplished at CSIR-NPL with the target uncertainty in solar cell current, that is ISTC. And when we compare internationally, our measurement capability among the world photovoltaic laboratories, scale laboratories, and NMIs, then this value in the uncertainty is the lowest. It means that we have the best facility to measure the photovoltaic current of the reference solar cell under standard test condition with the lowest uncertainty here. And this is achieved, then CSIR-NPL is going to provide the measurement with the lowest uncertainty among this world photovoltaic scale laboratories. And these services we are going to soon made open for customers, maybe January next year, to provide services to the stakeholders. The testing laboratories are the calibration laboratories in the country as well as neighboring countries, and certain some more add-on features is being added into the facility, as well as we are preparing the quality manual document, which is essential because this is a new facility added to the quality system of the laboratory NPL. Therefore, we should have a quality manual document for the facility, and which is being prepared. And as soon as this is prepared and we have an internal auditing of the system, we will be offering this service to the customer for the calibration of the reference solar cells in the country itself. No need to go to the abroad for their calibration. So the future roadmap for our PV metrology program in NPL is that we have planned to unveil the facility for the nation by January 2025. We are working on the required protocols and documents, as I mentioned, for the establishment of the primary standard facility for reference solar cell calibration and certification. The performance evaluation and comparison of the results with PTB and REL. PTB is done, and REL we will do. And then we will start dissemination of the calibration services to test labs and other stakeholders in the country and neighboring countries, thereafter. And this facility, I must say, that is of national importance, as I try to explain you, because the services of this facility is very, very much important in the ambit of national solar mission energy solar energy mission of government of India, and we should have as accurate as possible assessment of the performance. This facility will also help in self-sustainable quality infrastructure in the country for PV, because I mentioned so far the calibration of reference solar cell was done only by foreign countries. We had to send our reference cells to abroad. Sometimes it took 1 year, sometimes 9 months, and of course in foreign currency. So and transportation and is also another issue, and several problems. And this facility is not only is very, very useful in the success of the solar mission, uh, achieving the self-sustainable energy security, but also place the country one among the 4 world photovoltaic scale laboratories in the world. So the NPL would be the 4th in the world, and maybe the first in terms of lowest uncertainty in the measurement of the photovoltaic solar cell current in the standard test condition. So after achieving accomplishment of this primary facility and its dissemination, we will in future try to start the calibration of the secondary standard, development of the secondary standard, so that we can link this traceability chain right from primary through, of course, SI to primary and to the module, which are basically deployed in the field for the customers by the manufacturers. So with this, I basically end my talk. And I would like to, before I close, I would like to acknowledge the contribution and support by everyone. First of all the funding agencies, but first of all the MNRE, Ministry of New and Renewable Energy, Government of India, for sponsoring this primary facility establishment project. Then they, of course, CSIR-NPL, Council of Scientific and Industrial Research, DST for time-to-time funding in other projects and support. Then the PTB team, Germany team, mainly the Stephen Winter and Ingo Kroger, who basically were mainly involved in the development of this facility from the PTV side, and all the members of the photovoltaic metrology group at CSIR-NPL, Dr. Pratap Pati, who is PI of this project, Dr. Bandana, who was PI before she, took transfer to the MP Bhopal, and then Dr. Pratap Pati took over, and our present director, Professor Babu Gopal Achanta, he for director, CSR-NPL for all sort of supports, because it was a huge task, a huge challenge for us to get this facility installed, and he has played a tremendous role in motivating us and guiding us. Dr. D.K. Aswal, the former director NPL, and he played pivotal role in the movement of this project when it was sanctioned. He was the director, and he also played a key role in the success of this project. And then all the RC members of the CSIR NPL, previous as well as present, for all support and critical reviews and guidance time to time, and to have the smooth progress in this project and success. I would also like to acknowledge Dr. P.K. Singh, ex-chief scientist NPL, who is no more among us, unfortunately, but he actually conceived this project for NPL and started the formulating the project. I would also like to thank all the collaborators of NPL, like Tata Power Solar Systems Bangalore, Professor Vamsi Krishna of the Department of Energy Science and Engineering, IIT Delhi, and for all the collaborative works. Then I must acknowledge all the students who have contributed time to time in the success of different R&D projects, as well as this primary standard facility, and most of them are placed well in different sectors. So with this, I would like to thank everyone for your patient listening.
Sir, thank you very much for your brief and very innovative presentation. It is actually very important for the industry point of view, but my request will be if you kindly handhold the industry which want to develop this technology in the country, how to manufacture, how to test, then it will be very good. Even we are happy, actually we are happy, legal methodology is happy to come with you and do develop some type of facilities in our country if we can do.
Okay, sir. Thank you so much for your
Thank you. Thank you very much.
Definitely.
Thank you, sir. Thank you, all the participants. Thank you, Dikshit, sir. My national and the international participants. I'm very thankful to you. Next week, with the next topic, we will meet on next Saturday at 11 o'clock. Thank you very much. Thank you all. Bye. Good day.